All right. So if it's quantitative, then one of the things you want to think about is what kind of data am I going to end up with, so that I can be thinking about my analysis and things ahead of time. So you're always going to end up with some descriptive data from a statistical package. The first thing it will spew out will be a table that tells you how many people were in the database. If you put in ages, it'll give you an age range and a mean and a standard deviation from the mean. If you've got males and females, it'll tell you how many of each, or if you divide them up by any other grouping, you'll get all that kind of data out first. And then we're going to be looking for, remember, differences or relationships if it's a quantitative study. Can I find the relationship between these two variables, or can I find the difference between these two variables? All right. So I want my independent and my dependent variable. I want to know what level of data I've got. So remember, if your independent variable is a training program, right, then you may have two levels. You might have a dynamic stretch versus a static stretch. Right? So I would have two levels of my independent variable. I don't have two independent variables. And I want to be able to classify those variables. All right? I've got to know what's the independent. If it's a quantitative study, if it's a qualitative study, then you're not going to ID your independent and dependent variable in the same way. Okay. If it's a quantitative study, then you should be able to pinpoint your independent and dependent variable within your purpose statement. Okay. Which one's which?
Are you asking us?
Yes!
All right. So like for mine, since it's quantitative, both my variables would be lifting and the other variable would that be normal strength frequency.
Okay. And is that your independent variable or your dependent variable?
Would be my independent variable.
Independent variable because it's the thing you're manipulating. Right? Your dependent variable is the thing of interest. What am I trying to find out about? What am I using to manipulate that? He says he's not getting any audio again. And my audio's just turned off again. Wait, we just ran the wizard and it was going fine. I don't know what to do now.
Kind of cancel class.
At what point did that little, see, it says it's here. But it isn't, so the microphone should be right there next to my camera icon. in. Okay, so you, as master students, should only have one dependent variable and one at most, if you've got a really good argument, we'd let you have 2 independent variables, because the more variables there are, the more complicated the study becomes, the more difficult it is to control for external factors that might impact the results. Right? And we're looking for cause effect, so you can't say, well, I think, you know, if I had remembered to control for this variable, then my data might mean that, no. Right? So we've got to be very sure that we've identified those independent and dependent variables and that we know that we've controlled as best we can for everything else. Right? Once you know how many independent and dependent variables you have, you can use a very nice cheat sheet that my stats faculty member provided us when I did stats in grad school, and I've used it ever since. Right? So we have to say a big thank you to Dr. Garino, because his perspective was, your kinesiology students, you don't know how to do statistics and you don't need to hand calculate them. Yay! Right? Because you just stick everything into a software package and you press the button. The question though is which button? Right? So the cheat sheet helps you decide what is the appropriate statistical analysis for the type of data that you collected. Right? So, and there's quite a bit in your textbook on the different levels of data. I scanned in another sheet that was common statistical procedures from a different textbook. Right, so it gives you a whole list of different stats. So when you're reading articles, the more you read, the more you're going to start wanting to know what the stats meant. Right, so this will help you out with anything that you're reading. So on your cheat sheet then, if you look in the middle of the sheet, it's got a test guide. Okay. And so the first thing you want to do is define if your independent variable is continuous or categorical. So do I have an independent variable that I measure 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like speed? Or do I have an independent variable that is categorical? So I'm either in Group 1, Group 2, Group 3, right? If it's categorical and you only have 2 groups, then it's called dichotomous. So you might see that term as well. So once you've made the decision whether your independent variable measure is going to be a continuous number or a categorical number, then on column 1, and we're looking at univariate statistics because you only have a single dependent variable, right? Multivariate, the second half of this cheat sheet is looking at multivariate statistical analyses, and that's when you have more than one dependent variable. So you don't need to worry about that part of the sheet for your particular question, right? So I use column 1, and I've got some options depending upon how I classify that independent variable. Then I have to do the same thing for the dependent variable. Is the measure for the dependent variable going to be continuous, or is it going to be categorical? All right? And then I can put those 2 classifications together, and he gave us a nice list of then which statistical analysis I would use in that situation. And there are more complicated statistical analyses out there, and we'll talk in a minute about the fact that in order to use a lot of these, we have to have parametric data. We'll come back to that idea in a minute. But this does make it very easy, because now I plug all my data into a software package, and I tell it to run the analysis that is appropriate for that choice of variables. And it will do the run, it will spew out an output, and then you just have to interpret the output. You don't have to do the actual stats, which is very nice, because I also took a stats class with someone who thought everybody should hand calculate statistics. Ugh. Very ugly. The software is very nice. Whoever invented the software, thank you very, very, very much. And there's tons of different software packages out there. The one I used was SPSS, but there's lots of different software packages. Okay. Any questions on that? All right. So that will make your life way simpler. Right? So practice when you're reading. Right? Just practice classifying the variables in the articles that you're reading based upon the cheat sheet, because it's just whether or not you are going to write a thesis isn't really the question at this point. You are going to have to read a lot of research papers over the next year and a half. So you want to make that as easy as possible on yourself, and the more you know and the more you understand what is happening in the paper, the more enjoyable reading the papers will be. All right. Okay, so one of the things that we learn when we run the statistics is, what does the data look like? All right. So it'll have a shape, and if it is good, strong, normal data, it'll be a regular bell curve. All right? So it'll be, can you do me a favor, can you check the camera and see if I need to do this on the other side of the board? I can't remember where I have the camera pointed.
Yeah.
On the other side?
Yeah.
Okay.
Do you want me to just tilt the camera?
No, that's okay, I'll do it over here. Thank you. All right, so a normal bell curve, which I'm not very good at drawing, means that I have some data down here, I've got some data that lies on the other end, and the majority of my data sits in the middle in a nice normal curve. Right? It's one of the facts of data. Doesn't matter what you are looking at. Most data sits in the middle. Right? So if I'm measuring strength, most people aren't very weak or very strong. They sit in the middle. Right? If I am measuring height of trees, right? I'm going to have some trees that are very short and some trees that are ridiculously tall, like the things in Northern California, and most trees sit blob in the middle, right, within a range. Okay? If I have good normal data, then we can use any of the tests that we call parametric tests. But sometimes the data is skewed, and you should see that in the article. If they got skewed data, they should tell you. If they do a non-parametric test, which we'll come back to, and they don't tell you why, that's pretty weak, right? So one of the things that happens is the data can be skewed. So, that can mean that instead of having a normal bell curve, that my data comes out looking like that. Right? And the majority of my data is lumped to one side. Okay. Now, the one thing I used to have a huge amount, my particular phobia when it came to data shape, it took me forever. I would want to say that this was positive skew because the main part of the data was on the positive side of the graph, right? I had that in my head and it took me years to go, no, that's not right. This is a negative skew because the tail of the data points in the negative direction on an x-axis. Right? And they may tell you they had a positive skew, which is just the reverse, right? The large majority of the data lumped to the left-hand side of the curve, and the tail of the curve is pointing in the positive direction on an x-axis. All right? So, all you need to know right now, right? Don't get overwhelmed with this information, but you often see authors use that terminology. The data was skewed, therefore we ran this analysis. All right? So that's the only reason that you need to be realizing. Today's lecture is all about trying to make it easier for you to read data analysis choices and results. Okay? Not something you're going to have to do unless you do a thesis. The other terminology, although I have to say, in all the papers I have read, I have only ever seen this maybe once or twice. The other one is kurtosis. All right? And kurtosis means that your data is in the middle, but instead of being a nice bell shape, it comes in and it does this, more peaked or less peaked. All right. And as I said, I have hardly ever seen that terminology. Maybe it's just the kinds of papers. Maybe in chemistry papers you see kurtosis more often in the data, I don't know. Right? No. Chemistry expert goes, nah. All right? So you're not going to come across that very often. You will see skewed a lot. All right? Okay. So, why do we care what shape the curve is? So, which analysis we use depends upon this curve, right? If we're going to use a parametric test, so an ANOVA, a t-test are parametric tests that you'll see a lot of in PE kinesiology type papers. A lot of people use t-tests and ANOVAs of one form or another. Then there are some assumptions that are made about the data if you use those tests. One is that the data is interval data, so the variance between each point on the curve is relatively equal. Right? And more to the point, the easier one to understand, I think, is that we've got a normal curve. So you might see a paper perhaps that said we were going to run a t-test, but when we looked at the data and the data was skewed, we decided that we needed to run a chi-square. Right? So again, it's less about anything you would have to do and more about helping you just try to follow the terminology in a research paper. If the assumptions aren't met, so if your data points are haphazard and randomly spaced, or if your data is skewed, positive or negative, or if you have kurtosis, but as I said, I haven't hardly ever seen that, then you're going to use a non-parametric test. On page 327 in your book, there's a table of those. I also have the other book that I use a lot for this lecture is Research Techniques for Health Sciences, and they have a whole lot of information about non-parametric tests, so chi-square, Mann-Whitney, Wilcoxon, matched pairs. So these are all terms you may see instead of a t-test or a repeated measures ANOVA. All right. They're not wrong, they just allow for the fact that the data wasn't normal. All right. Now, some authorities say that if you had to use a non-parametric test, that's a little bit weaker than if you use a parametric test, that somewhere in your data planning you didn't make sure about something that would have given you didn't control for something, and so your data came out skewed. Right? So if you put all your strong athletes in one group and all your weaker athletes in another group, your data might come out skewed because you didn't randomly assign your strength and you're looking at strength as a variable, possibly, right? So you would have to use a non-parametric test to test the data, but some people would say, well, you should have planned the distribution of your participants more strongly. Does that make sense?
Yeah.
Okay, so right, just keep thinking about those results sections or the end of your introductions and the methodologies where they say, here's the data analysis that we used. Here's our hypothesis is another term that you're going to see. And there's lots of different ways of telling the reader about your hypothesis. So it may be called the research hypothesis, it may be called H1, right? The research hypothesis is your statement of what you think is going to happen based on your question and all the reading that you've done about the question. All right, so my research hypothesis would be, if I run this motor skill intervention, I'll see improved catching scores in 6-year-olds. Right? Because according to all the literature I've read, if I run the intervention well, I should see improved scores. So that would be my research hypothesis. Right? So it's giving a statement of the difference or the relationship between the participants, the variables, and that we're going to find the difference. Right? That the relationship is going to be significant, or that the difference between these two things is going to be significant. Right? Significance is a statistical term. We don't mean significant because it's important to you, although it does incorporate the idea of importance mathematically. Right? The other one, so you might see them state their research hypothesis, or they might state the reverse, which is called the null hypothesis. They may say the null hypothesis is that my intervention won't make any difference and I won't see any change in catching scores for these children. Right? Obviously, for most of us, when we're running a study, what we want to happen is what we think was going to happen, right? Because that's why we ran the study. We had this idea, we thought that perhaps this might make a difference, and so we run the study with that in mind, right? So we hope to reject the null and accept the research hypothesis, right? That's our goal when we run the statistics. Right? I want to reject the null hypothesis because the null hypothesis says there wasn't any difference. So 2 negatives make a positive. If I reject a no difference, I'm saying there's a difference. Yes? Okay. How do we do that then? Okay. So on the papers you've already read this semester that were quantitative, you saw, if you were looking, you saw a symbol P. Right? Typically less than, sometimes less than or equal to a number. Right? P is the value of alpha. Right? Alpha, you might see written as alpha, you may see it in the paper as an alpha symbol. Right? The probability, alpha is the probability of your finding being correct. And it has to be set a priori. That means before you run the data analysis. It should be set before you collect the data. It should be part of your planning, your design, right? This is part of my study. The alpha is going to be set at whatever. Right? I have to say, I have seen people change alpha after the effect because they didn't get any significance, and if they change alpha, they do get significance, and then it's a stronger study to report. That's cheating. Cheating. Do not do that. Okay? So, the test that you pick is going to have alpha set at a level. Typically for kinesiology studies, that is going to be 0.05. If it's a sociology study, it might be 0.1. If it's a drug study, it might be 0.01. Okay? So, the probability, the alpha gives you the probability that the null hypothesis is going to be true, right? That there's no significance. So I want it as small as possible. Okay. I want to be able to reject the null hypothesis. I want the biggest probability possible that my data and my significance is accurate. I really, really found a difference. Okay. So when you see P at 0.05, alpha was set at 5%, that means that there's a 95% probability that the difference, the significance I found was real and not accidental, not by chance. Because however much I control for everything, I could still get a result by chance. Okay. So if I set it at 0.05, alpha's 5%, I have a 95. If I get P less than 0.05, that's significant. That's a 95% chance that my finding was right. That's very nice, right? 95% probability that this training program works better than another training program. That's a pretty good win for me as a coach. So, why would we set it not at 0.05 but at 0.1 or 0.01? Alright? So, remember this is giving me an idea whether I can reject or accept the null hypothesis. So, if I set it at 0.1, that means that whether I find significance or not is interesting, it's relevant, no one's going to get hurt, right? I had a 90% chance of being right. So, if I'm looking at does my coach buying us pizza make his athletes like him more, I would set P at 0.1, because really, right? Does it matter? Yes, because obviously you want your athletes to like working with the coach, and that might motivate them more, and that might help them play better. But if it's wrong, it's not going to kill anybody. Right? Now, when do I set it at 0.01 then? So if I'm a chemical company and I've developed a new drug that I think is going to stop people having a heart attack, and I have to test it. Okay. And they put the drug on the market, and they tell you that they're 95% certain that this will stop you having a heart attack, not cause you to have a heart attack. Is that good enough? Right? Are you going to buy that drug? Right? They're only 95% sure it's going to cure me, not kill me. I don't think so. Right? So when we're looking at something like that, we set P at 0.01 because now my outcome is 99% certain. Right? If I say the drug is going to cure you, not kill you, I'm 99% sure. I'm still not sure that that's good enough, but statistically you could see 0.005. I never have, but I don't read those kinds of studies. Right? And then I'm 99.5% sure that the drug is going to cure you. You're never going to get 100%. We want to get as close as we can. Does that make sense? It's a little bit mathy, but it's important because if you are reading a study about a training program, a flexibility program, or a supplement, or a drink, a Gatorade type drink, or something like that, and they tell you that alpha was set at 0.1, I'm not sure I would waste my time reading the paper. Right? It's up to you to make that decision. I wouldn't read the paper if they set alpha at 0.1. Because that's not a sociology study. You telling me if I use this drink, it will improve my performance in my training. Then I want to see 95%. Right? So that's why it's not anything to panic, but it's just a little bit of math to help you decide, is the paper relevant? Is it doing what they said they set out to do? Are they setting their testing at an appropriate level? Because when you read that conclusion statement at the bottom of the paper, and they go, oh yeah, we know for sure that this blue drink does more than the yellow drink. Do they really? What did they do? Right? Question?
So you want to look at something more?
Most sports science, PE type intervention studies use 0.05. Now, sometimes they'll go to 0.01 because the smaller the number, the bigger the impact factor of the outcome. They might set it at 0.05 a priori, but if they get 0.01 in their results, because when you get the table spewed out of the software package, it will tell you what the significance was, right? So if you find something that's 0.01, trust me, they'll tell you, because that means it's really cool, right? I have seen people set it at 0.05 and not find a significant difference, and then when they write the paper up, they say they set it at 0.1, but that's cheating. But I have seen that done, sadly. All right. So connected with that idea is the type of error you're at risk of making as a researcher. There's always error. The question is, can I make a good error rather than a bad error, right? So a type 1 error is worse. And it's worse because if I make a type 1 error, that means I rejected the null hypothesis. So remember, the null hypothesis means I don't find a difference. I reject that. I say I did find a difference when actually no difference existed. I misinterpreted the data. That's a type 1 error. That's bad because if I'm rejecting something that is true, then that means my results are garbage, right? Because I'm telling everybody my results are important and they're not because there was no difference, right? So is there a difference in running 100 meters with spikes or in tennis shoes? Right. The research hypothesis would be yes, I would expect to see a difference. The null hypothesis would be there's no difference in those shoes, and that's true. and I said it isn't true. Right? Type 2 error is preferable because a type 2 error, if I'm going to make an error, is less dramatic. I'm less likely to hurt someone if I make the type 2 error. The type 2 error means that I say I didn't find any difference, I accept the null hypothesis, when actually a difference did exist. So it is typically thought that a type 2 is the preferable error because I'm less likely to damage someone if I say I didn't find a difference. One of the terms you'll see people often use is how much power their data had. They might say that they ran a power analysis before they decided how many participants they needed. Right? So, one of the reasons one of my papers was rejected was because it didn't have enough power. I only had 25 kids in it and they wanted 150. Well, I didn't have access to 150, so there wasn't anything I could do about that. I didn't pick 25, that was who I had, right? So power means that you're less likely to make this type 2 error. The more powerful the data is, often power is dictated by the number of participants, but not always, right? So you might see them say, we did not meet significance, although the trend in the data was towards significance, and we believe if we increase the power of the study, we would find significance if we reran it. Right? Does that make sense? So it's all about finding significance that counts for something. Finding significance that counts for something. So, if I run a study and, let me think, I find a significant difference of, so I'm going to use your traditional, I keep using his study because it's very easy in my brain to relate to. I'm going to use a traditional weight training program, or I'm going to use a HIIT, high intensity program, or a Olympic lift program, right? And when I analyze my data, I find a significant difference, and the Olympic lifting program was significantly different, higher than the typical weight training program, right? Then when I look at the data, the significance is 1 pound. Does that make any difference at all to how well that player is going to play? No, right? So it could be mathematically significant without having any practical influence at all. So one of the things you want to look for when you're reading, if it's a really good study, they will report the effect size. The effect size represents the practical importance, the practical strength of the significant result. If they use the term effect size, then you would probably they would use the measure that 0.2, less than 0.2 is a small effect size. So they might say we found significance, but the effect size was only 0.16, and so the effect for practical purposes is quite small. Or they may say P was less than 0.05 and our effect size was 0.84, which is huge, and this study's really, really, really cool and important, right? It will make a massive difference to your training program. Okay? Effect size, let's see what else. You might see, they might actually call it an effect size, they might run, they might call it a correlation coefficient, and then it's, I think it's an R squared. If it's a correlation coefficient, that's the same thing as an effect size, just a different version. What's the variance explain? Right? How strong is this result? So the more power the study has, the greater ability there'll be to get a big effect size if one exists. Can I detect an effect size? The more power I have, the more likely I am to see if an effect size exists. And you want medium or large is good when you're looking at effect sizes. Eta squared is another term for effect size. R squared, you might see Cohen's D. They're all terms for effect sizes. Just depends which type of analysis and which kind of data you're looking at. Yay! I think that's the last slide. All right, so as I say, my goal for this lecture, this is not something that you will immediately use in this class, other than it should make reading these articles easier for you, right? If we still had the second research class, you would use it to the extent that you have to write chapter 3, your methodology, and you would have to decide what your alpha was going to be, which analysis you were going to run, okay? And then if you were going to collect that data, then it becomes really important, okay? So for now, this is FYI, stick it under your hat, use it as information to help with reading, because there are times even now, actually especially now because I don't read enough research anymore, but there are times, and I know certainly when I was at your level, when I was in my first semester, I used to skip the results section completely. I would read the intro and the method and the discussion, and I wouldn't even look at the results section. And you can get by with that to a certain extent, but at some point you've got to know what they're doing and why they think their conclusion is relevant. Because sometimes the conclusion is wrong based on the data they collected and the test that they ran. So it's foundational info more than using content. This is not going to be content for you. Questions? Greg, do you have any questions? I don't know if you can hear me now. You're okay? All right. Okay, so remember Thursday, your ANOBIB 1 is due. It should be a concise paragraph for each reference, up to 275 words, I think I said, not including your citation. So your paragraph, you have 275 words.
For each reference?
Yes.
How many references?
4. You do not, all right, the article summaries that we did before midterm were formatted in that template in a deliberate attempt to get you to learn about what kinds of articles you were reading. So, if you are doing an ANOBIB, you do not write, this was a lit review, right? That's not a relevant piece of information to put in an ANOBIB, because if you do the ANOBIB, if you summarize the paper correctly, the reader knows it was a lit review. Right? My reason for having that on the template was I wanted you to start identifying the different kinds of articles that were out there. You may not necessarily state the purpose statement. It depends how close the purpose statement is to the article title. So that one's a little bit iffy. You probably aren't going to bother telling me which statistical analysis, because it depends on how well you're able to shrink down to 275 words, because that's quite a lot less now. Right? You don't always have to say they ran a repeated measures ANOVA, because the important thing is, did they find significance, and what did they conclude? So you can use your judgment. The data analysis is sometimes in an ANOBIB and sometimes not. It's not a mandatory piece of information. Right? Do I need to know how many participants there were? Yes. Do I need to know if they were male or female? Depends on what the title and the purpose were. Are they analysing men and women separately, or are they analysing one whole group? Right? Go for it. There's a whole second chance at that ANOBIB later on anyway. So get it in. All right? Here's the thing, it's better to send it in and get a crappy grade than not send it in, because 0 is worse than any crappy grade. I've never yet given anyone like a 0 on an ANOBIB. You'd have to basically not hand in the ANOBIB, right? So approach it that way. Anything you hand in means you get feedback back, which means the next one will be better. Okay. All right.
Do you want me to stop this?
It must be time for some food. Yes, please. Thank you. Okay, Greg.